Okay, so in this video we're looking at exercise 1E, question 1 to 6 of the proof by exhaustion chapter. We're beginning by looking at the green questions, and let's start off with question 1 that says prove that 11 is a prime number through proof by exhaustion. Now, of course, a prime number is a number that has exactly two factors, which are the number 1 times by the number itself, in this case 1 and 11. Now you could, because 11 here is a really small number, you could just go and work your way through the other integers and go 11 divided by 2, 11 divided by 3, divided by 4, by 5, by 6, all the way up to 10. And you would see that if you divide through by those numbers, you get decimals, therefore 11 is a prime number. But we saw also previously on the first video on this topic that you want to make things as quick as possible for yourself. So if we are a little bit crafty about this and we go and think, well, what is the square root of 11 equal to? It is approximately equal to 3.3, roughly. Okay, so if we just go and consider the factors that are less than, okay, so that are less than 4, okay, if there are no factors of the number 11 that are less than 4, that must mean that there are no factors of 11 greater than 4. Because if there were to be a factor less than 4, you should be able to multiply it by a factor bigger than 4 to make the number 11. So if that is not the case, if there's not a factor less than 4, okay, we can just say 11 must be a prime number. So let's do that. Okay, so we only need to go and consider two numbers here, dividing through by the number 2 and by the number 3. So if we go and do 11 divided by the number 2, 11 divided by 2 is equal to 5.5. Therefore, okay, 2 is not a factor. Okay, and it seems really obvious, doesn't it? But I'm just writing everything out really clearly. Mathematical communication is really important. So 2 is not a factor. Okay, good. If we go and do 11 divided by 3, okay, that is equal to, what's that equal to? 3.6 recurring? 3.6 recurring. Anyway, the key thing there is 3 is also not a factor. Okay, excellent. Look, and if you wanted to, right, you could go and divide 3 by 4, by 5, by 6, by 7, by 8, by 9, by 10, but you're wasting time because we can now go and state, the following, which is this, right? As there are no factors less than the square root of 11, i.e. less than 4, okay, that implies, that must mean that there are no factors greater than the square root of 11. Okay, and the reason for that being is, right, if there were a factor less than the square root of 11, there isn't. If there was, that must then mean there would be a factor bigger than the square root of 11, i.e. bigger than 4, that when you times them together, you get 11. But that isn't the case. We can see, well, there are no factors less than the square root of 11 or less than 4, which we saw by 2 and 3, which implies there are no factors greater than the root of 11. Therefore, or thus, okay, that must mean that 11 is a prime number. Okay, so there we go. So you can see there, right, that's quite a simple question, I think, with proof by exhaustion, but actually quite a lot of written mathematical communication there, okay? But I'm making it really, really clear with all of my sort of reasoning what is going on there. I'm not just sort of kind of scribbling something down. It's like a logical argument. Okay. Question 2. Very similar, isn't it? Which is now saying that prove that 83 is a prime number. And again, right, we're going to be doing this in a very, very similar way. And this one, it is really, really important that we're not just going through, dividing through by, because again, if 83 is prime, it must have only two factors, which are the number 1 times by the number itself, 83. It would be crazy to go and divide through by 2, 3, 4, 5, 6, all the way up to 82. You'd be wasting a lot of time. So again, let's go and consider the square root of 83, and that's approximately equal to, what is that approximately equal to? 9.1. Okay, so if we just go and consider the integers or the factors which are less than 10, okay, well, if there were to be a factor less than 10, that must mean that there must be a factor bigger than 10, that if you multiply those numbers together, you get 83. Okay, so if there are no factors less than or equal to 10, that must mean that 83 is a prime number. So I just need to go and consider my integers, not even all of my integers, as you'll see in a second, that are below the number 10. Okay, let's go and do that. So let's go and do 83 divided by the number 2 to begin with, and 83 divided by 2 is 41.5, okay, which of course means that 2 is not a factor. Okay, and then let's go and divide by our next integer, which is dividing 3 by 3. So let's go and do 83 divided by 3. And what does that equal to? 83 divided by 3 is equal to 27.6 recurring, okay, which again is a decimal, so it can't be a factor. So 3 is not a factor. Okay, do I need to go and consider my integer 4? No, because if 2 was not a factor of 83, because 4 is a multiple of 2, 4 won't be a factor of 83. So I go and consider my next number, which is the number 5. Okay, I can go and do 83. Let's keep it in red. Let's go and do 83 divided by 5, and let's see what that's equal to. It's going to be equal to a decimal, isn't it? 83 divided by 5, 16.6. Okay, therefore, your number 5 is not a factor. Again, do I need to go and consider my number 6? No, because if 2 is not a factor of 83, because 6 is a multiple of 2, 6 won't be a factor. So then I go and consider my number 7. So I go and do 87 divided by the number 7, okay, which again will give you a decimal, but let's go and write out what that's going to be. 12.4. So again, 7 cannot be a factor because if you divide through by it, you get a decimal. So 7 is not a factor. Okay, do I need to go and through divide by the number 8? I don't, because if 2 is not a factor, 8 will be a factor. Do I need to go and divide by the number 9? Well, no, because 3 is not a factor and 9 is a multiple of 3. Therefore, 9 will also not be a factor. So I've considered all of my integers that are less than 10. And I've seen, okay, that if I divide through by 2, 3, 5, and 7, okay, I get decimals, which means that I have no factors less than 10. Which mean that there are no factors bigger than 10. Okay, therefore 83 is going to be a prime number. So let's write that out again. So because, let's go and write it in blue. Let's go and write it in green actually. Right, because there are no factors less than the square root of 83. Okay, there are no factors less than the square root of 83. That implies, and that must mean, okay, that there are no factors greater than the square root of 83. Because again, if there were to be a factor less than the square root of 83 or less than 10, there must be a factor bigger than the square root of 83, bigger than 10. If you multiply those numbers together, you get 83. But there isn't in this case, as we've just shown over here. Therefore, thus 83 is a prime number. Thus 83 is prime. Okay, excellent. So again, you know, I think proof is quite nice, right? The more that you kind of see these questions, the more, of course, familiar you come with them, but it's just really important, right? Mathematical communication, that you're telling a story with your working. Okay, hopefully you can follow this along and it does make sense. Okay. Good. Question 3. What is this question saying? It is saying that prove that all regular polygons with fewer than 7 sides have angles with a whole number of degrees. So we're looking at prove that all regular polygons with fewer than 7 sides, okay, have angles with a whole number of degrees. Right, with this question, because we're not really going to be considering too many polygons here, if you're considering polygons with less than 7 sides, fewer than 7 sides, you're considering a polygon with 3 sides, with 4 sides, with 5 sides, or with 6 sides. So I'm literally just going to go through all of the possible variations, and that's going to be good for this. So that's going to be when your number of sides is going to be equal to 3. Okay. Number of sides is equal to 4, so a triangle, a quadrilateral, a pentagon, and a hexagon. Okay, so it won't take too much time. Let's go through this. So right, and then to find and let's make a bit of a table here. There we go. Bam. Okay, excellent. And to find the sum of the interior angles in a polygon, okay, the formula back from GCSE is n take away 2, and you times by 180. Because remember, this n take away 2, it tells you how many triangles you can get in a polygon, okay, and then you times how many triangles you can get with that, the degrees in each triangle. So just to quickly recap that, just to go back a little bit where this formula actually comes from. Let's just say we're considering a pentagon, so 5 sides. Okay, so like this, there we go. Okay, this formula is saying that is, God, crikey, so it's very early in the morning, right? What am I doing there? There we go. Let's make it a bit symmetrical. Excellent. So this bit here, n minus 2, is saying, well, if your number of sides in this case is 5, pentagon 5 sides, if you take away 2, it is saying you can make 3 triangles from this shape. So you can, from one point, you can go and make 3 triangles. Okay, so you can see you've got 1, 2, 3 triangles. So n would be 5, take away 2 gives you 3, times it by 180, 3 by 180 would give you 540. Okay, so this is the sum of the interior angles of a polygon. That is just explaining where it comes from a little bit. Anyway, let's go through our cases. So the first one, if the number of sides is equal to 3, we're going to be having 3, let's keep it in red, sorry. We're going to be having 3 take away 2 times 180 is equal to just 180, right? There's 180 degrees in a triangle in a 3-sided shape, which hopefully makes sense, which is good. Let's just put a bit of a line up here. Let's do it in black. There we go. Excellent, good. Our next one is going to be, we've got now 4 take away 2. So 4 take away 2 times 180 is equal to 2 times 180 is equal to 360, which makes sense, right? In a 4-sided shape, in a quadrilateral, we have 360 degrees. Good. In a 5-sided shape, it's going to be 5 take away 2, like the pentagon over here, times by 180. Right, it's going to be 3 times 180, which is equal to 540 degrees. And a 6-sided shape, we're going to be 6 take away 2 times by 180, okay, which is going to be equal to 720 degrees. Right, okay. Right, but we're trying to prove that have angles with a whole number of degrees. Right, this is telling you the sum, so this, add this, add this, add this, add this, of the angles in your polygon. We want to find the individual angles. So you want to go and divide by the number of sides. Okay, so you want to go and divide this formula by n, because that tells you the individual angles in each of the polygons. So let's go and create an extra column in our table. Okay, so I'm literally going through all of the possible variations, okay, that I can have here. So then up here, I'm going to be writing, so the sum of the interior angles, which was that formula, and take away 2 times 180, and if you go and divide by your number of sides, okay, divide it through by n, that will tell you what the individual angle is worth in your polygons. Okay, so the first one, doing 180 divided by the number of sides, which is 3, so 180 divided by 3 is going to be equal to 60, okay, and then you can see whole number of degrees, which is good. Your next one, we're doing 360 divided by your number of sides, okay, which is 4. So 360 divided by 4 is equal to 90. Then doing 540 divided by your number of sides, which is 5, which is equal to 108. Last but not least, we're doing 720 divided by your number of sides, which is equal to 6, which is equal to 120. Okay, so you can see here, degrees, that all of these angles, 60, 90, 108, and 120, they have a whole number of degrees. So I've been through all of the possible variations, okay, to prove this statement by exhaustion. Okay, using a table to help me with my proof in this question. Okay, question number 4 says, prove that no square number less than 100 ends in a 7. So let's just go through our square numbers and let's see if they end in a 7. They don't, but we've got to go and show that, so let's go and do that. So our first one is going to be 1 squared. Well, that's equal to 1. Doesn't end in a 7, so good. Let's go through 2 squared. So sometimes with proof by exhaustion, okay, you just want to go through all of the examples because actually it is quite quick to do so. We saw on the first 2 questions, we wanted to make things a little bit quicker. Sometimes you just go through all of them because it's just the easier thing to do, like in question 3 and 4. 2 squared is equal to 4. Okay, 3 squared is equal to 9. You know, we keep going through them. Okay, excellent. 7 squared, 49, go up here, 8 squared, 64, 9 squared is equal to 81. And you can see, okay, these end digits, 1, 4, 9, 6, 5, 6, 9, 4, and 1, none of these end in A7. So literally I've gone through all of the square numbers less than 100 to prove that none of your numbers end with a 7. Okay, excellent. Question number 5 is this. So let f of x be the function that gives the number of factors of x. So for example, f of 10 is equal to 4 because the number 10 has the factors 1, 2, 5, and 10. So you can see that there are 4 factors. Okay, excellent. Prove that for any single digit, positive number f of n is less than or equal to n. So it's just saying, basically go through all of your single digit integers, so 1, 2, 3, 4, 5, 6, 7, 8, and 9, and prove that the number of factors is either the same as the number or less than that number. Okay, so if we just go and consider our single digit numbers, okay, so let's make a bit of a table here going from n, going up from 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then below, we're going to have f of n, okay, and we're going to show that the number of factors, okay, is either equal to the number itself, okay, so less than or equal to, or less than that number. So this is telling us how many factors, right, our numbers have got. So for the number 1, well, how many factors has the number 1 got? Well, you've just got 1 times 1, so you've got 1 factor. Okay, so 1 can go in there. Brilliant. So you can see that that is either less than or equal to the number itself. 1 factor is the same as the number itself. The number 2 has got 2 factors, which are 1 and 2, and that's it. So we can see that this one, it has 2 factors, which is 2. So again, you can see that the number of factors is 2 is either less than or equal to the number itself, which is good. Your next one, 3, again, it's got 2 factors, 1 times by 3. So you can see that again, your number of factors is equal to 2. So this time, okay, we've got a number, the number of factors is less than, which is fine, our number. So that's good. We've then got the number 4, which has got 3 factors because it's a square number. You've got 1 times by 4, and you've got 2 times by 2. So you can see the number of factors here is equal to 3, which again is less than our number itself, which is fine. You've then got the number 5, which has only got 2 factors because it's prime, 1 times 5. So this has got 2 factors. You've then got the number 6, which has got 4 factors, 1 times by 6 and 2 times by 3. So this number, we've got 4 factors, which again is fine because that is less than, the number of factors is less than the number itself. The number 7, again, is prime, 2 factors, which are 1 times by 7. So that's good. 2 factors, good. We've then got number 8, which has got 4 factors, 1 and 8, 2 and 4. And last but not least, we've got the number, sorry, let's put in number of factors there, which is equal to 4. And then we've got the number 9, which has got a square number, 3 factors, so 1 times by 9 and 3 times by 3. So this number has got 3 factors. So important, you can see that the number of factors that our single digit numbers have got 1 to 9 have either less than or equal to the number of factors, have factors either less than or equal to the number itself, which we can see down here below. So I've gone through all of the possible variations. I proved it by exhaustion. Excellent. Question number 6. Is this proof that n squared plus 2 is not divisible by 4 for the integers 1, 2 to 5? Again, because we're not considering many integers here, it's probably just a good idea just to create a bit of a table, okay, and just to go through our integers. Okay, so let's go and do that. So so some integers n, 1 through to 5, so 1, 2, 3, 4, 5, okay, and we've got n squared plus 2, so we're creating a bit of a table here again. Okay, so we talked about in the opening video that when you're proving something, okay, you want to create kind of like a logical argument, either using algebra we talked about a little bit, but also by using other methods. So we're using tables quite a lot in this video, which is nice, okay, which is fine. Let's go across. Let's make this quite neat. There we go. Good. Okay. That will do. That's okay. So, but n is 1, n squared plus 2 is going to be 1 squared plus 2, which is equal to 3. Ooh, let's keep it in red. So 3, n is equal to 2. 2 squared is 4 plus 2 is 6. 9 plus 2 is 11. 16 plus 2 is 18. 5 squared plus 2 is equal to 27. Okay, and if we divide these by 4, so if we go and take n squared plus 2 and we divide it by 4, okay, we will see hopefully that we get decimal answers, which we will do because, well, 3 divided by 4 gives you 0.75, 3/4. We've then got 6 divided by 4, okay, which gives you 1.5, okay, which again is a decimal, so not divisible by 4. We've then got 11 divided by 4, which is equal to 3.75, again, which is not a integer. We've then got 18 divided by 4, which is equal to 4.5, which again is not an integer. And then we've got 27 divided by 4, which is equal to, what's that equal to? 27 divided by 4, 6.75. Okay, so there we go. Okay, I can see that all of these numbers here clearly are not divisible. So 0.75, 1.5, 3.75, 4.5, 6.75, because they are all decimals, okay, they are not divisible by the number 4. I've been through literally all of the outcomes. I've proved this by exhaustion. And I think, is that it for this video? That is it. Okay, excellent. So hopefully that was useful. And then we'll get on to what questions we're on to next. Question 7 and 8, and then question number 9. Thank you.